Hi everyone, my name is Celine Turfloth. I manage the Aquaponics system on campus. This is my third time advising an island school, aquaponics research team, and this semester we kind of decided to switch things up a little bit and start looking into aquaponic crop diversity, which has everything to do with campus food security initiatives. I've had such a blast delving into this pretty novel research with my co-advisor and these budding food security advocates.
Hi everyone, I'm Alex Cook. This is my fourth year on the Island School faculty and fourth overall research project that I've advised, and I'm really excited for our team to share what they've been up to with you guys this semester.
Welcome to Aquaponics. My name is Sienna Henderson.
My name's Annie Muja.
My name's Matt Arrigo.
My name's Tucker Simonson.
My name's Ali Kimball.
My name's Casey Pope.
And my name's Delilah Paulino.
And we will be focusing on increasing tomato plant production using beta buckets and mineralization. So for those of you who don't know what aquaponics is, we're going to start off with a definition. Can anyone tell me what hydroponics is? Any hands?
Water and soil.
Yeah, so basically plant production using no soil. Does anyone remember what aquaculture is from previous presentations? Yeah, exactly. So the farming of aquatic animals. So aquaponics is the combination of both aquaculture and hydroponics. It's a closed recirculating system that uses the nutrients from fish waste to further nourish plant growth. Our aquaponics system at the Island School started in 2005 as a method to start fruiting vegetables. There are many significant benefits to aquaponics. Compared to traditional planting, aquaponics produces 150 to 200% more food per square foot. It also only uses 5 to 10% of the water needed versus soil-based plant production. Aside from the economical and sustainable benefits of aquaponics, it also has the potential to improve both food security and nutrition. Fish is the fastest growing industry for food globally. In 2007, it accounted for 17% of the global intake of all animal protein, and that stat still stands true for 2017. Fish also contain essential micronutrients and vital amino acids, and they're a great resource for low-income families. Because the land of the Bahamas is primarily made out of limestone, it makes it extremely hard for agricultural production, and due to this lack of agricultural production, the Bahamas faces both food scarcity and economic stress. Nearly $1 billion is spent annually on food importation in the Bahamas.
Our overarching goal in aquaponics is to be a model for sustainability and to improve food security at the Island School and throughout Bahamas as a whole. Currently, the Island School imports 89% of their food, which means that the Island School is 89% food insecure. I'm going to repeat that. The Island School is 89% food insecure. However, the aquaponics team has harvested over 500 pounds of lettuce since the start of the semester. So not only are we trying to make lettuce sustainable on campus, we are also trying to increase fruiting vegetables like tomatoes. By increasing our production in tomatoes, we will hopefully decrease the need for importation and therefore lower our carbon footprint. However, in order to achieve these goals, we're going to use two different methods called mineralization and the beta bucket system. We are hoping that with the use of mineralization and the beta bucket system, we will get the results we need to make the Island School a more sustainable campus.
So currently all of our leafy greens are grown in a raft-based deep water culture system. This is a great system for plants that don't require as much root structure. However, with sun gold cherry tomatoes, they require a lot of root structure, making a media-based solution more favorable. So we chose to use a beta bucket system with media. The beta bucket system is a media-based form of growing plants in which the media retains water and also acts as more structure for the roots to grow. This leads to more productive and healthy plants. So in our system, we have 3 different types of media: coconut husk, clay pellets, and pumice. Coconut husk is made by us shredding coconut waste, and it has great surface area and retains water well. The other 2, clay pellets and pumice, must be imported and mined, making it much less sustainable. However, the greater surface area offers better aeration. So in our system, we have one irrigation line that feeds directly from the raft system and waters all the plants. At the bottom of the buckets, we have water valves that let all the excess water out of the buckets. We have 9 buckets. 3 of them contain plants that were grown for 1 month in the raft system, while the other 6 contain plants that were started in the Beto bucket system. Also in the raft system, we have 2 plants acting as a control. Weekly, we'll measure the plants, count the fruits and number of flowers, and reference this to the controls to see if our experiment is working.
So Matt touched on the physical alterations we make to our system to improve fruit and vegetable growth, and I'm going to continue on this topic and elaborate more on the chemical side. In an aquaponics system, wastewater flows through a biofilter to convert fish waste and ammonia from it into nitrates that can later be taken from the water by plants, thus cleaning the water for fish. While this may be beneficial for leafy greens such as kale and lettuce, we are focusing on a mineralization system to improve micronutrients for fruiting vegetables such as tomatoes. Mineralization, which you can see here, our 15-gallon mineralization vessel, is defined as the bacterial degradation of fish waste using oxygen to liberate trapped nutrients. In English, this means fish waste is broken down by bacteria using oxygen. While this may sound like quite a complex system, it's actually relatively simple. Each day, we take 1 gallon of mineralized water after letting solids settle to the bottom from the mineralization vessel and manually empty it into our overall aquaponics system. Then we take 1 gallon of fish waste and put it into the mineralization vessel. Background research done by Ricosi suggests that mineralization vessels can improve macronutrients such as potassium, calcium, and phosphorus essential for fruiting vegetable growth, such as our tomato. Every other day, we test for 6 macronutrient levels: phosphorus, potassium, calcium, ammonia, and nitrate. I believe that's all. I think I got all 6.
So this graph demonstrates the results of our Beto bucket system. The x-axis is the growing media, the y-axis is the mean growth in centimeters, and these error bars here represent the standard error, which is simply the variation of data within each treatment. As you can tell, the mean growth of the 3 medias were all higher than the mean growth of the RAS system, proving that our Beto bucket system was successful. However, there was a relatively high standard error, and that can potentially be accounted for by 2 things. The first being that we had a very small sample size, so 1 outlier would have totally skewed our data. Furthermore, this graph groups together the mean growth of plants that were at different stages of growth. So some were seedlings while others had previously been in the RAF system, which could also add discrepancy to our data. Moving on to the results of our mineralization vessel, these 4 graphs demonstrate that. We have the x-axis is days, and the y-axis is the nutrient in parts per million. As you can see in the key here, the smaller dashed line is the mineralized water, the larger dashed line is the system water, and the horizontal line is the recommended nutrient concentration for tomatoes. In the 2 graphs on the right, which illustrate nitrogen and phosphorus, the mineralized water and the system water were quite close in proximity throughout the 8 days of trials, proving that there wasn't a very significant difference between the 2 water sources. However, in calcium, which is in the top left, the mineralized water was consistently higher than the system water, proving that the mineralization vessel had some sort of effect on the levels of calcium. Finally, for potassium, we had an unforeseen challenge in that we only got 3 days of data before our test kit ran out, simply because there was much more potassium in our system than originally anticipated. So while the mineralized water was consistently higher than the system water, there simply is not enough data to make a thorough conclusion.
As Elliot had mentioned, the tomatoes that were grown in the Beto bucket system were far more successful than the ones grown in the traditional RAF system. However, these plants were bullish, meaning they were very vegetative, but were lacking ripe fruit. Our theory behind this is that there's a nutrient imbalance, specifically our NPK, nitrogen, phosphorus, potassium ratio, was not ideal for fruiting at this plant stage in its life. We had hoped to correct for this through mineralization, however, this process was not exactly beneficial. As we can see right here, our nitrogen and phosphorus levels were not near that recommended concentration, but specifically for nitrogen, this is not a huge issue, because if that nitrogen level was up at the recommended concentration, it would not sustain fish life, which is a very important part of our system. On the other hand, we have calcium and potassium. which are right on par with the recommended concentrations. Potassium, those levels surprised us because potassium is typically lacking in an aquaponics system, and as of now, we do not have a reason behind those high potassium levels. Calcium, on the other hand, we could have predicted because the water in our system comes from a well, and well water is considered to be hard water because of the dissolved minerals in it, one of which is calcium. Potential reasons for this have to do with the frequency at which we are emptying our mineralization vessel, which can be compared to an experiment conducted by Ricosi in 2007 at the University of the Virgin Islands, where they had a mineralization vessel that was left untouched for 29 days, whereas we remove 1 gallon of mineralized water from our system every day.
In conclusion, based on the data collected and presented by the aquaponics team, the mineralization vessel and the beta buckets did not produce the anticipated results hoped for. Although there is something to say for our beta buckets as a system when compared to our controls. Our beta bucket plants are far healthier than our controls. The only flaw in our beta bucket system is the lack of tomatoes, or specifically red tomatoes. As of recently, there are some red tomatoes, but just, again, not as much as we anticipated. This might be, as Casey mentioned, because of an incorrect NPK ratio. In the future, aquaponics hopes to continue upon the existing systems and improving them, as well as creating new systems to improve the NPK ratio. This might mean using a foliar feed, which is a direct add-on to our tomato plants specifically, that will give them the correct amount of nutrients. Aquaponics also hopes to continue being the main supplier of lettuce at the island school, as well as continue research into other forms of plant production to further our overarching goal of food security on campus. This is our literature cited. We'd like to acknowledge Celine Turfloth and Alex Cook, our advisors, as well as Donovan Hepburn and Walter Neely for being just as big of a help as our advisors. We'd also like to attribute our success in APON to the comms team, the permaculture team, the CEI, CSD, as well as Kate Kincaid. Do you guys have any questions?
So the question is whether weather could have affected our plant production and the amount of tomatoes that we got in our beta bucket system. And the answer is yes. However, the weather has actually been pretty nice considering it's supposed to be a lot hotter and it's supposed to be a lot sunnier right now in Bahamas. So technically, actually, there should have been more tomatoes and a higher plant production because in the summertime, we only produce about 30% of the lettuce that goes to the dining hall, whereas right now we're producing 99% of lettuce that goes right to the dining hall. So weather definitely plays a big role in it, but as of right now, that shouldn't have affected it too much.
You mentioned in other studies you saw 29 days. You've had only a similar 24-hour period of time. What do you think was the next biggest barrier to your research beyond not just having the extended period of time in order to be able to observe the chemical change?
So the question was, aside from our
Outside of time, what was the next biggest barrier, do you think?
So outside of time, for the mineralization vessel specifically, what was our biggest barrier in our project? Personally, I would say the size of our mineralization vessel. So as I said, if you can click back a couple slides, please. Thank you. Yeah, this mineralization vessel is only 15 gallons versus other vessels which were much larger, and as you said, the time was definitely a big factor. So size of the mineralization vessel would probably be the next biggest factor.
Could you clarify your statement that the excessive levels of nitrogen and phosphorus being fish? Does that mean that you're actually recycling the water at some point back into the aquaculture?
Yeah, so the question was, just to clarify, for the nitrogen and phosphorus levels, he said that the levels, well, we basically said that the levels were very high or they were not very high because otherwise it would have killed the fish. And so yes, it does circulate back in. That's the beauty of the aquaponics system, is that the waste of one side of it goes in and is used as a resource for the other side. So the plants filter the water, and that water goes back into the fish tanks, and then the fish poop, and that provides nutrients for the plants. Yep.
So it seems as though this system requires lots of constant maintenance. Is there any hope that this could be somewhat self-sufficient in the future? Or like more easily accessible for more people that don't necessarily have that much time on their hands?
The question was, is there a possibility that the aquaponics system could become more self-sufficient in the future? And just comparatively to a normal agricultural method, it's relatively comparable, and even if the aquaponics system does require more maintenance, it's kind of a trade-off that we think is definitely worth it because of all the pros to aquaponics. It provides a lot of agriculture without needing soil or like very pertinent weather conditions. So I think the trade-off is definitely worth it. Yes, Mom.
I'm wondering how many fish you had put on those giant tanks, and then also did you consider something that is mostly with leafy greens, maybe address kale or chard or other things that would benefit from an excess leafiness and not leaf benefit?
Wait, could you repeat that question again?
Just how many fish, like the number of fish that you have?
Well, so the question was how many fish we have and if we've considered focusing on leafy greens. So currently we have 730 tilapia in our system. It's a lot of fish, yeah. And to answer the leafy green question, currently we provide the island school with 99% of their greens, like lettuce, kale, microgreens, which is great, and that's during the winter months and the spring months. The summer months it's a little bit lower because it gets really hot. Yeah. Yeah. Yeah, Mom.
So the first question is for you. So you didn't like tomatoes before you came to island school?
True.
Second is, why tilapia? Is there, have you tried different fish? Is there better, maybe higher nitrates in the water with different fish?
I still don't like tomatoes, to answer that first question.
So we have tilapia in the system because they can tolerate very high, varying levels of nutrients and are hardy. Mom?
Do your greens or tomatoes attract any pests and bugs? And if so, how do you manage that without affecting the water that goes back to the fish?
So the question was, do our leafy greens attract any bugs, and how do we manage that without affecting the water or the fish?
So there are a lot of bugs that fly around within our raft system, and generally we just leave them there unless there's like a behemoth. But all in all, we just leave them there and let them be. They don't really have a huge effect on our production.
We do pick off caterpillars if we see them though. But if you do see one in your salad, don't be too surprised.